is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at our other gas laws. Up to this point, we've only really looked at the ideal gas law, but we've had a conversation about how varying particular components like pressure or varying volume, how it's going to affect other variables while we hold some things constant. So the one thing that I definitely want to start off right at the bat with the ideal gas law is for you to understand that the ideal gas law is actually a snapshot, right? I'm not varying anything with the ideal gas law, right? I'm just holding and saying, hey, I have this pressure, I have this volume, I have this temperature, how many moles do I have, right? And so that's the ideal gas law. But the ideal gas law can be used to reason and actually figure out the other gas laws that we need to know. So what I'm going to do is I'm going to start out by giving you the ideal gas law. And I'm going to ask that you make sure that you understand the difference of, hey, when I'm going to vary pressure, I'm not using Pivnert, but I can use Pivnert to actually determine what I will do to figure out what's going on quantitatively. So there's 4 different situations that we're going to look at. And I'm going to go ahead and draw all of these lines out here, right? And separate my page into 4 different areas. And so I'm going to draw a line over here just to make sure that I don't go out of bounds over here and you can't see what I'm writing. Okay, so my 4 situations that I'll run into is I'm going to hold constant our number of moles and temperature. Or on this one, I'm going to hold constant my number of moles and pressure. Over here, my constants will be pressure and temperature. And then over here, we're going to hold constant our number of moles and our volume. So those are the 4 different situations that we're going to take a look at. So remember, and you've seen a lot of this so far, ladies and gentlemen, remember if I'm going to hold number of moles and temperature constant, then PV equals nRT, this ends up being constant, right? And that's what we used originally to say that pressure and volume were inversely related. Now, what we're going to do now is we're going to actually assign a law to it. So this is known as Boyle's law, and he's the one that actually figured out this relationship. And so we need to understand that if I've got pressure and volume inversely related, that if I do pressure volume equals a constant, well, that's going to also equal any other pressure volume combination. So notice now what I'm going to do is I'm going to apply 1s and 2s. Well, it's really important to understand what the 1 and 2 designation actually mean. The 1s mean this is what I'm starting with, and the 2s is this is what it is after I've changed something. And so, but notice, because of the way Pivnert works, they're all actually going to be equal to the same thing. So what we do is we just get rid of the constant and say that P1 V1 equals P2 V2. All right? And inversely related, if I was going to graph that, I'm just going to draw the graph really small down here. And so a volume versus pressure graph in this particular case would give me an inverse relationship line. Right? And it's important to understand, Boyle's law is the only one that's inversely related. Everything else that we looked at was actually directly related. They're the only opposites. And that's an easy memory trick to remember. Hey, Boyle's law, when I'm trying to make these predictions, the only inverse relationship that I should see. It's the only one whose graph looks like this. All right? Okay. So the next one, I'm going to look at if I've got a constant number of moles and pressure, what does Pivnert actually look like? Well, I'm just going to show you what it looks like after I solved it out, right? So nR over P, this ends up being my constant, and then that would be times my temperature. And so notice, if I increase volume, I have to increase temperature, and so that's why we say volume is proportional to temperature. And so that's the proportional sign that you're seeing there, all right? So who's this? This is actually known as Charles's law. Right? And Charles's law says we're going to write it this way because it's a little bit more friendly. So volume 1, volume 2 divided by temperature 1, volume 1 divided by temperature 1 is equal to a constant, and that's the same thing, volume 2 times or divided by temperature 2 is also equal to that constant, and that's known as Charles' law's equation. So V1 over T1 equals V2 over T2 is where we get that from. Now, the graph on this particular one, if I graph volume versus temperature, it's just a straight line, right? And that's a straight line right there. Okay, because it's a direct relationship. If one goes up, the other one proportionally goes up, and we see that because it exists that way because of this ratio to volume to temperature. If I increase volume, I have to also increase temperature to keep this ratio of volume to temperature the same. All right? Okay, moving on. The next one that we will take a look at, find a color here, is if we hold pressure and temperature constant. And so again, I'm just going to move everything around in the ideal gas law, right? So it's, again, we see volume and number of moles. If I increase volume, I need to increase the number of moles. So we would say volume is proportional to the number of moles. Whose is this? This is actually known as Avogadro's law, right? Because again, we're dealing with the number of moles here. And so in this particular case, again, to rearrange to make it nice and friendly, V1 over N1 equals some constant value, which means V2 over N2 also equals that value. And so we simplify this, V1 over N1 equals V2 over N2. And again, just to make a small little sketch down here at the bottom, volume over number of moles, it also would be a linear relationship. So again, notice Charles' law and Avogadro's law, linear relationships increasing vertically, and Boyle's law is the only one that sees that negative inverse relationship, right? Okay, so the very last one that we're going to take a look at, let's do a green color over here. So I'm going to hold number of moles and volume constant, So number of moles and volume present, I keep present because I see P. All right, so constant. So I've got NR over V, and then so this is my constant value, so that'd be T. So you can see increasing pressure should increase temperature, and so we say pressure is proportional to temperature, right? And this is known as Gay-Lussac's law. All right, and so again, pressure 1 over temperature 1 is equal to some constant value, so that means pressure 2 over temperature 2 is also equal to that same constant value, and I can set them equal to each other. So P1 over T1 equals P2 over T2, and again, just to give a small little sketch, because I'm running out of room here, this is going to be temperature down at the bottom, ladies and gentlemen, and it would be a vertical positive linear relationship as well. All right? Okay, so that was a lot, ladies and gentlemen. Look for the commonalities in here. And again, remember the ones versus the twos. I'm using these gas laws here, Boyle's, Charles, Avogadro's, and Gay-Lussac's, when I'm varying something, right? I'd hold something constant, I'd change one of the variables, and ask, how does it affect the other, right? That's different from the ideal gas law because the ideal gas law is a snapshot. I'm not changing anything. I'm just saying, under these conditions, what do I have, all right? Okay, so if you have any questions, get them down. I'll see you in tutorials for those. Otherwise, I will see you in class.